Welcome, builders. So, you're tuning into this Forge College Explainer, and today we are unfolding the blueprints for our capstone project in the Solidity from Zero track. Specifically, we're talking about library strategies and integration. If you've ever stared at your smart contract and realized it's gotten so massive and repetitive that it basically needs its own zip code, well, you're in exactly the right place. Let's figure out how to keep things clean, secure, and incredibly efficient.
Okay, let's map out our agenda for today. 1. From planning to composition. 2. Internal versus external helpers. 3. Wiring your smart contract. 4. Defending the boundaries. And 5. The verification checkpoint. Let's just dive right in. Section 1. From planning to composition.
So here's where we stand in the process. In our previous lesson, we drew up the plans and tackled project planning. Today, we're in the current phase, which is library integration. We're taking those prefabricated parts and putting them together. And next up, we'll run some rigorous diagnostics with debugging and testing.
Section 2. Internal versus external helpers. Let's establish what a library actually is in Solidity. Basically, they're reusable blocks of code that isolate specialized logic from your primary contract operations. Think about it like this. A monolithic smart contract is kind of like lugging around a giant 100-pound Swiss Army knife. I mean, it's just way too heavy. Instead, we use libraries to outsource that logic, which cuts down on duplication and makes everything so much easier to audit. Now, we've got two main flavors here. First, internal libraries. These are your tightly controlled defensive math fortresses, and they are kept strictly in-house. External libraries, on the other hand, are imported, lightweight utilities. You use these external ones for tedious cross-project jobs like string formatting. Section 3. Wiring your smart contract. Okay, so how do we actually wire these helpers up? Well, we rely on a few really practical integration patterns. We use direct library imports, we utilize the using for directive, and this is absolutely crucial. We prefer pure or view functions. Why pure? Because mutating state inside a library introduces complex context switching and, honestly, totally unpredictable gas costs. Keeping them pure just makes your life infinitely easier. Now, what's really fascinating is this using for directive. When you declare using helper libs for uint 256, it seamlessly attaches your library functions directly to that variable type. So instead of awkwardly passing an integer into a function like you're stuffing a package into a mailbox, your standard integers literally get custom helper methods attached right to them. It kind of feels like magic, but it makes the code wonderfully clean. Let's look at how we wire specific roles. We connect our internal safe-add library to a mutating deposit function. Since deposit actually changes state and handles user funds, it really needs that tightly controlled embedded math. Conversely, our external format uint library hooks up to a read-only formatted balance function. It's just displaying text, right? So a lightweight external helper is the absolute perfect tool for that job. Section 4. Defending the boundaries. Now that we're wired up, we need to talk about the library boundary. This is the precise point where your main contract logic hands off data to the helper logic. You've got to treat bad user inputs like hazardous materials. You definitely do not want garbage data entering your delicate library machinery, because you're going to get catastrophic results. So there's a vital rule of thumb here. Place defensive checks near the library boundary. The strategy is simple. Let the library do the math, but let the contract guard the gates. If your pure library has preconditions, like expecting a number to be below a certain limit, you must check that right before you hand the data over. We do this by setting up defensive require statements, like require amount greater than 0, capstone amount must be positive. This stops arithmetic overflows or zero-address disasters dead in their tracks. And notice that explicit error string? That's going to save you countless hours of head-scratching when a transaction inevitably fails. You'll know exactly which boundary was tripped. Section 5. The verification checkpoint. We never blindly push code. We verify. Here is our minimalist local testing checklist. First, compilation. We expect absolutely no errors. Second, library usage. We confirm our methods are actually being invoked. And third, input validation. We ensure all preconditions are met before any state changes happen. When we execute our local compile script to simulate a user deposit, it is incredibly satisfying to see our formatted balance return exactly 1,000. Seeing this cleanly formatted output confirms that the wiring is absolutely perfect. So our compilation was successful, our require statements are thoroughly tested, and our gas footprint is observed. That last part is key, by the way. External and internal libraries actually consume gas differently, so keeping an eye on your gas footprint now means we get no expensive surprises down the road. We've built an incredible fortified scaffold today, but here is the big question. What happens when our perfectly wired libraries encounter truly chaotic, unexpected user behavior out in the wild? Can your contract survive a failed require statement buried deep within a complex call stack? To find out how to debug those issues and to learn a whole lot more about Web3, head over to Forge College to continue your journey with this Forge College series. Keep building, stay curious, and I'll catch you in the next explainer.